Hey everybody, welcome back to another video within the Generative AI series. And in this video, we'll be talking about how we can store embeddings into ChromaDB. Now, ChromaDB happens to be an open source embedding database. So up till now, we know what embeddings are, what like in a more verbose term, what vector embeddings are. We know how to evaluate similarity between multiple vector embeddings by using cosine similarity. We know how to generate vector embeddings using OpenAI. But the example or a demonstration that we worked upon in the last video happens to be very basic. So we just created an array through in some sentences. We had a query string and we generated and evaluated the cosine similarity upon the embeddings that we got. But in real life scenarios, we'll be dealing with huge images, huge videos, and huge documents. So we need to create vector embeddings for these entities and store them somewhere. Obviously, we cannot store everything within the memory. We need some sort of a persistence when we sort of generate these embeddings. So hence, that's where ChromaDB sort of comes into the equation. So as the introduction states, ChromaDB makes it easy to build LLM apps by making knowledge, facts, and skills pluggable for LLMs. And here's a little depiction in terms of a diagram. So you can create as many documents in text, or you can even store embeddings directly if you have already generated them. But what we want is we want to encapsulate this whole process. We don't want to generate embeddings ourselves, per se. So what ChromaDB offers, that whenever you feed in documents, whenever you feed in text strings, it automatically uses an embedding function to sort of convert them into embeddings. And you can query these embeddings directly, or you can query these embeddings through text, which is sort of a huge plus for us and a huge convenience. Alongside, Chroma gives you the tools to store embeddings and their metadata. Yes, if you have documents and text documents, and if you have some additional information that you wish to store, so you can also do that. For example, if you're generating an embedding out of a PDF book, so you can store the author's name, some bio about the author within the metadata and stuff like that, which you can also leverage in terms of searching through LLMs. So yeah, Chroma prioritizes simplicity and developer productivity, exactly something that we are looking for. Analysis on top of search. It also happens to be very quick. So let's get started with it. So we have a huge support in terms of Python here. We'll just go ahead and pip install ChromaDB. We'll create a ChromaDB client, pretty similar to OpenAI. And if you're familiar with NoSQL and its terminology, then it's exactly the same with vector databases as well. So you create a collection would be the database name, and you can add some text documents to these collections. So here's an example. Currently these documents are in form of strings, and within the metadata you can store their sources individually. Obviously these corresponds to each other. What it requires, which is like a cherry on the top, is that you'll have to provide some unique identifiers for each of the documents that you have. And as stated here, you can even store embeddings directly, but that's not something that we need. And you can query your embeddings just like that, just by giving the text, just like how normal databases work. So this is great. I mean, creates a bunch of convenience for us. So in terms of usage guide, I want to talk about collections, and within collections, now the question is, and you might be wondering about it as well, like if we provide in the text document, how does it sort of generates the embeddings by itself? So that's the question I'm going to answer through their documentation. So the embedding function takes text as input and performs tokenizations and embeddings if no embedding function is supplied. So you can sort of supply your own embedding function, but if you don't, Chroma will use the sentence transformer as default. So it's like a great library, and it's built upon BERT networks. You can even use this individually, but the good thing is ChromaDB already uses it. So that's a huge plus as well. And alongside that, another thing that I want to talk about is like, so we talked about cosine similarity, and I want to talk about changing the distance function. So in our case, we've been using cosine similarity as a distance function within our last video. And if you haven't seen it, I'm just going to hook it up into the info cards. Go check it out. You'll learn plenty out of it. But moving forward, cosine similarity is not the only distance parameter or distance function that you can use. So as you can see, you have a bunch of other functions over here. You have squared L2, you have inner product, which is more like a generalization of dot product. So let's talk about that a bit. I really want you guys to understand this bit before we move forward. Or in the world of LLMs and in the world of vector databases, you should have a clear concept about what cosine similarity is, what a dot product actually provides you in terms of a property that you can use in your evaluations and processing, and what squared L2, what L2 norm is. So let's talk about that a bit. All right, so these are the distance metrics in vector search. So first and very foremost is cosine distance. You might be wondering, this looks a bit different than what we have discussed. Yes, it is. So what we have discussed is cosine similarity. So it depends on the sort of the angle between these two vectors. So the formula for cosine similarity is all about finding that angular property. But cosine distance sort of spins it around and creates a scalar property which refers to a distance. Now, when you actually are using cosine distance, your values are from 0 to 2, where 0 is actually your two vectors are pretty similar, and 2 specifies they are dissimilar. So cosine distance is used in terms of, having that balance or sort of visualizing that a bit properly in terms of dissimilarity and similarity. So dot product is like when you have two vectors, so you project one vector upon the other vector to see the magnitude of it. Like if they're really similar, obviously you would get a very strong value against it. So just remember it that in a dot product, or a more generalized form, which is the inner product, you're projecting one vector upon the other, and that sort of determines how similar these two vectors can be. And dot product is like the foundational way through which you can actually evaluate similarity, and everything else is sort of built upon it. As you can see, even in cosine distance, you're actually using a dot product. So squared Euclidean L2 squared, which is something that is being offered right here. So what this is like, it's a way of sort of computing a distance between 2 points in a vector space, or two vectors. And then you have an L1, which is also called Manhattan. And as you can see, that this sort of computes distance as well, but it's more like a bit edgy, squarish and edgy. Obviously, L2 squared is a better distance metric than Manhattan, but it also exists. I mean, just for the sake of knowledge. So just remember these formulas. You have it right here. You can screenshot them. You can write it somewhere, or just for the sake of remembrance, you can just know that what they actually signify, right? And that would be enough. So, all right. So yeah, that's pretty much it. But just to be a bit more elaborative, I have another screenshot where you can learn what L2 norm basically is. So the L2 norm, also known as Euclidean norm of a vector, is specified like this. And squared L2 norm, and both of these actually refer to squared L2. So squared L2 norm, squaring the L2 norm simply involves squaring each component before summing them up. So this is just like a bit of more information of what L2 norm basically is. So as you can see, it's a way of sort of finding out the magnitude of a particular vector. So yep, I hope it's pretty much clear now.